And first, this module won't be in your midterm test. Midterm test only study for the first 4 modules. Modules 1, 2, 3, 4. Okay? So we leave 5 and 6 to the final. All right. But one thing, because you look at the topic, indexing and complex queries. Yeah, look at this. Here we have the complex queries. Yeah. In our homework assignment number 2, we will practice a few questions in this complex queries. Practice. Yeah. But in the midterm, I won't give you complex queries. Okay? Basic queries. So we leave complex queries to the final. Yeah. But in our homework assignment number 2, we need to practice a little bit. Yeah. So we just do practice. Yeah. So you need to spend some time, study, improve, get yourself better on complex queries. So then in the final, we will do 5 questions on, related to complex queries. All right, so let's start. Part A, Introduction to Index. Yeah. In this part, we will study an important topic, index. Index, yeah, so there is a special technique in DBMS. In DBMS, indices, using indices to improve the search performance. So here in this introduction part, let me explain the basic ideas of this technology or technique. Yeah, because it's a, all right. Yeah. All right. All right. Yeah, so let me just connect it. All right. .1, why using indices? Yeah. All right. Speed up the retrieval of records in response to certain search conditions. Here, think about when we have large database. We have many tables, and some of the tables could be very large number of rows. When you do the search operation on this big database, how to get the records very fast? Especially, think about, especially your database may contain the data in several gigabytes. Okay, that large. But we want to get a very fast response. In order to do that, we need some help. We need some special algorithms to help us get faster performance. All right, so that's the reason. So this technology is important. Technique is important. Yeah. All right. But how to do it? How to do it? Yeah. So let me talk about the details. First, the idea. The high-level idea, how to improve your search performance. Yeah. The structure of the data is important for the performance of data retrieval. Yeah. So here, the data. So when you enter the data into the original table, original tables, so you have the original data, the structure of data there, but the original structure may not be friendly for fast search operations. May not be friendly. Why not friendly? For example, the data is not sorted. Original data in a table, usually not sorted because the data is entered randomly, not following any specific order. Okay? Yeah. But you know, if the data is not sorted, when you do the search operation, you need to do the sequential search. Yeah. So here, just the basic knowledge from the algorithm. Yeah. For unordered data, unordered, right? All right. When you do the search, basically you can only do the linear search, right? Or sequential search algorithm. Yeah. Here we need some knowledge from our algorithms, but the basic part. And for the linear search, we know the performance we have is the big theta of n. If we use the asymptotic notation, big theta of n, okay? Asymptotic notation. This n data size, here you can treat as the number of rows. Yeah. Number of rows, actually more than that. Yeah, because your row may contain a lot of fields, right? Now here, we just use the number of rows for our understanding. Yeah. Then, this is for unordered data. But for ordered data, if the data is sorted, for ordered data, we can apply binary search, right? It is much faster than the linear search. And using the asymptotic notation, the performance we have is log of n. From n, big theta of n, to big theta of log n. Good improvement, right? Big improvement. Yeah. Why big improvement here? I just give you some idea. For some of you, let me just recall a little bit from our algorithm course. The improvement, if n equals 2 to the 10th, that is 1024, but the log base 2 of n equals 10. Look at the big difference. If you use linear search, you may need 1,000 comparisons. Yeah, let's say just 1,000 comparisons. Yeah, or average 500, right? Because you may argue we use the average efficiency, not worst case 1,024. Okay, average 500, let's say, but binary search, the worst case. This is the worst case. Log base 2 of n, 10. From 500 to 10, that's big difference, right? Yeah, but 1,000, it's not a big number. You can imagine 1 million. Think about 1 million, all right?
Yeah. If 1 million, that's m, equals 10 to the 6th, right? 1 million. Yeah. That's approximately 2 to the 20th, right? 2 to the 20th. Yeah. Then log of base 2, think about log of base 2, 20. Okay. From 1 million comparison to 20 comparisons. How big improvement it is, think about. That's the huge difference between linear search and the binary search. Okay. And we want to use binary search. Yeah. But the original data, original table, the data is not sorted. You cannot apply binary search. All right. Yeah. And think about if you want to do the sorting before you do the search, that's very expensive. We know the sorting operation is very expensive. Okay. Yeah. Very slow, very expensive. Yeah. So then a new technique we need to use, we need to make our data ordered based on some specific field. Because we have many fields in a table. When you say ordered, based on which field it is ordered, it's different, right? Yeah. Yeah. So here you need to consider different fields. You want to make it ordered. After that, you can take advantage of the binary search to make your search operation very fast. That's the high level. The motivation. Yeah. Why we need to consider some special algorithm to improve the search operation. Yeah. So that's the motivation. All right. Yeah. So let's look at the details. Yeah. So here, but the original structure of data should not be changed. Yeah. All right. So here, look at this. We want to make our data based on a specific field ordered, but we do not want to change the data in our original table. We do not want to change the original data in the table. Yeah. Yeah. So this requirement also important. We want to maintain the original table structure. Okay. Yeah. That means we should use auxiliary, secondary, auxiliary structure supporting our current table structure. We add extra structure. Yeah, we can use supporting extra data, supporting data to make our search operation faster. Yeah. Yeah. So another point. Yeah. All right. Yeah. So, yeah. I mean, original structure may not support good performance because you can only do linear search, right? Yeah. So it won't be fast. Yeah. Usually it's not ordered. Yeah. So we need to add auxiliary supporting files, also files, okay? Supporting auxiliary files, physical files, all right? Physical files, yeah. Not virtual files, yeah, here, physical files, all right? Yeah. Create auxiliary access structures, and that structure, that newly added structure, we call it indices. We call it indices. Okay, physical files, indices, physical files. Yeah. All right, files, remember long time ago when I talk about the meaning of the files, meaning tables, right? One file corresponds to one table in our DBMS. Here, one index corresponds to one file. That one file is a special table. Okay, special table. Physical file special table stored in the hard disk. In the hard disk. Yeah. Okay. Then I describe the structure of the index files, supporting files. Okay. Yeah. All right. Based on indexing fields, you need to select indexing field. Yeah, just one field. Okay, because you need to do sorting. After you select an indexing field, yeah, DBMS will do the sorting for you. All right, you do not need to worry about it. Okay, you just tell DBMS, I want to select this field as an index. Now, one index, create index using this field. So DBMS will create auxiliary data and do the sorting, make it ordered. Yeah, you cannot see it. Yeah. The DBMS just do it for you. You do not need to see it, right? Why you need to see it? You do not need to see it, okay? Yeah, it's not important. It's internal files. Yeah. We as users, we should not touch it. If you touch it, if you modify, you may break it, right? And it won't work when the DBMS try to do the binary search, but you break it. And it won't work. So DBMS does not allow you to touch it, right? You just tell DBMS, I want to select this field as my index. Okay, yeah. And you can declare multiple indexes, not just one, because we have several fields. Okay, so we may need multiple indexes for one table, multiple indexes for one table. Okay, yeah, all right. Right, yeah, here, multiple indexes on different fields for the same file, same table. Then, because later when you do the query, you may want to have the fast performance binary search on different fields using different index files. Right, yeah, okay, yeah. All right. Yeah, so here, the basic idea, so you can understand why binary search is so useful. Yeah. Yeah. Here, it's a big application of the binary search. Yeah. All right, so here, when I use the asymptotic notation, the binary search, we use the asymptotic notation. Yeah, remember this log base 2 of n. All right, yeah. That's the approximation representation. Yeah. So later, yeah, because later I may ask you the worst case of the binary search, worst case. Yeah. When you know the number of rows, we know n, number of records here. N means number of records in the table. All right, yeah. Then I may ask you, yeah, later I will talk about this again, but here I just, the worst case, the number comparison, we have a exact formula, not approximate, exact formula, because usually people use the approximate formula, but here I give you the exact formula. All right, yeah, that is log base 2 parenthesis n plus 1 seeding function. That's the worst case, the number of comparisons for the worst case for the binary search. This formula. Yeah. Okay, yeah. Remember that plus 1, n plus 1. Yeah. Because when you have, here, when you have the records, n equals 2 to the k minus 1, then this formula would give you, you have this many records, would give you the number of comparisons, k. Worst. Yeah, because plus 1 to the k. Then take log base 2k. Okay? But think about, if you do not use the plus 1, then you have k minus 1, right? Not k, k minus 1. Okay? Yeah, so that's the difference. One comparison difference. All right? Yeah. All right. Yeah. Index basics. Now we need to learn the internal data structure. How do we arrange the data inside the hard drive to make our index-based search very fast? Yeah. So that kind of detail. Yeah. Secondary access paths. Supporting secondary. Okay, yeah, not primary. Yeah, all right. We need additional files on disk. Yeah, I already mentioned. Yeah. Using extra storage space in exchange for better performance. Yeah. So you need to use more space. Yeah, all right. But that extra space, first, you will see the index file relatively smaller. Comparing with the original file, much, much smaller. Yeah, won't be very big. Yeah. So that relatively small amount of extra space used can improve search performance a lot. So we are willing to spend, we are willing to use that extra storage space. Yeah. All right, yeah. Sorting can be used in those, right? Binary search, sorting. But DBMS does the sorting internally. Yeah. You may not be aware of the sorting operation. Yeah. The DBMS does the sorting, in a hidden way. Okay? Hidden way. Nobody can see it. Nobody can be aware of it. It just happens. It happens behind the scene. Okay? Yeah. All right. Does not affect the physical placement of records in the primary data file. Yeah. Your original data won't be changed because your original data reflect your business situation. So you don't want to change that. You don't want, because although fast search performance is important, but you don't want to change the, your business related data. Okay, yeah. So you want your data in the tables directly reflect your business process. Okay, yeah, yeah. But this technique allows you to do that. Yeah, so don't worry. Yeah. Indexing fields. All right. Let's consider if we need any special requirements on the indexing fields. Requirements. Okay, yeah. Basically, any field of the file can be used to create an index. Basically, any. there must be some exception. Any field. So we need to put some specific requirement there. Here. Yeah. If no requirement, but that requirement is very easy to be satisfied. So that's the reason it's a basically any field. Yeah. So it's some, very simple requirement. Yeah. Yeah. We will see that. All right. So not necessarily those fields with total ordering. Yeah. Not necessarily those fields. Here, the concept total ordering. Total ordering or total order, partial order. Yeah, so here, the two concepts. So here, the concept. Related to order, when we talk about order, total order and a partial order. Right. Here, total order. The usual order we understand, that's the total order. Total order, any two elements in the domain can be compared. That's the total order, right? Yeah. So any two elements in the domain. Yeah. So here, because we consider some special domain. Yeah. Can be ordered. Yeah, let me write, can be ordered. So you can determine one is bigger than the other. That's the total order. But partial order, not that. Partial order, some of the elements you can compare in order, but some of the elements you cannot compare in order. Okay, yeah, partial. All right, yeah, all right, partial. Yeah. Here, let me describe the partial. Yeah, so here, yeah. Some, yeah, only some. Can be ordered, all right? But some other cannot. Yeah. But it's hard to imagine, right? So here I just use a simple diagram to show you that situation, right? Suppose I use some graph, simple graph to describe this idea. Okay, all right. I use arrow to define order. Yeah. If A greater than B, I use an arrow, one arrow from A point to B. That tells us A greater than B, okay? Then another arrow, B greater than C, another arrow, B greater than C. Yeah. Then we define, because A greater than B and B greater than C, by the transitivity property of inequality, A should be greater than C, right? Yeah. Transitivity, yeah. So partial order must satisfy the transitivity property, okay? Yeah, this property. Property for this partial order, yeah, must satisfy that. But here, let me assume there is another element called D. Yeah. We can define A greater than D, another arrow from A point to D. And D greater than C, another arrow point from D to C. But look at B and D. Is there an order between them? B and D, no order. Because there is no arrow from B to D, and there is no arrow from D to B. right? So this kind of relationship, we call it, we have a partial order, not total order. Because B and D cannot be compared. When you do comparison, we don't know which one is larger, which one is smaller. Right? Yeah. Yeah. So look at this special situation. That could happen. That could happen. Yeah, here. But here, the indexing field, not necessarily those fields with total order, no problem. You can apply comparison, you can get sorted, right? Yeah. But here, think about this special case. Not necessary those fields with total order. Let's assume some field does not have total order. If a field does not have total order, can you sort it? You cannot, because only when you have a total order you can sort it, right? Otherwise you cannot. Okay, yeah. So without total order you cannot do sorting. But so the sorting based index files cannot be created, but we can use another technique to create an index. We do not use sorting. We use another technique. Okay. Yeah. So think about. Yeah. So here, let me write this way. Yeah. Let me write this way. If no total order for a field, that means the data cannot be sorted based on this field. Based on this field. But we still want to create an index file to make the search operation very fast. In this situation, we need to use another searching algorithm, fast searching algorithm. Not based on binary search. We cannot do binary search. Another searching algorithm, hashing. Hashing. In algorithms, we know hashing. Okay, hashing. Yeah, I will explain the. Yeah, although we learned the hashing technique in algorithms, but I believe some of you may forget the details of this hashing technique. Yeah, later at some time I will basic idea and the basic structure of hashing. Yeah, very simple, but extremely fast. Even faster than binary search, hashing based search. Yeah. Yeah. Hashing technique, yeah, faster than binary search. The operation is big O of 1. This is the average case. Average case, big O of 1. The number of comparisons. Think about even you have large number of records, rows, large number of rows on average. Okay, yeah, on average, 1, 2, 3, several comparisons, but on average, big O of 1, that number of comparisons. Really fast, hashing. Okay, yeah. without total order, we can still use the hashing technique. Okay, yeah. So that's the reason you have this here. Okay, not necessarily those fields with total order. Yeah. Yeah. All right. Yeah. Yeah, I will give you a little more details on hashing. Yeah. Yeah. But we do not need to know too much details, right? Just the basic idea. That's enough. Yeah. All right. Some index do not use sorting. Yeah, the hashing. Okay. Yeah. All right. 8.2 data structures for indexing. Yeah. All right. Look at that. More details. Yeah. Ordered files. Order the files, then binary search. Otherwise, hashing. Okay. Yeah. Require total ordering. Total order. Okay. Total order. Total ordering. Yeah. Use the binary search. Okay. Right. Most prevalent types of it. Yeah. Because most of the time our data has the total order, right? Yeah. String data, alphabetic order, numeric data, natural order, in numbers, data, we have order. We define order, date, right? Yeah. Other than that, so most of the data we use in our daily life, they all have order, total order, let's say. Yeah. But not 100%. Yeah. You may have 90-something%. Yeah. Or even you can say 99% of the time. But you have very small percentage. Yeah. You may not have the total order. Yeah. Don't worry, no total order. Yeah. So the DBMS can apply that hashing technique. Hashing technique. Yeah. Yeah. But here, yeah, yeah, because usually you do not ask me questions. So here I just think about the possible questions you may ask me. Think about if you have this kind of questions. Yeah. All right. First, we know the binary search. We have the search performance. That is big theta of log base 2 of n, and the hashing big O of 1, the average case. Yeah, yeah. Actually, the average also in this category, right? Yeah. Although we say worst, but average also in that category. All right. So here, you may argue because hashing is faster than binary search. Hashing is faster than the binary search. Some of you may want to ask me, why not just, we always use hashing, then we can do faster. Yeah. Actually, the answer is no. You cannot make your decision just based on the asymptotic notations you see here, because hashing is applied on data without order, without total order. That means no ordered data available for this technique. Yeah. You lose the order information. Yeah. But when we use the binary search, we can maintain the order information. But with hashing, we cannot, nothing to do with order. You lose the order information. Okay? Yeah. That's the reason if your original data has the total order, it's better to use that binary search based index files, because you can always do the sorting. When you need to do the sorting, it's fast. It's very simple. Yeah. Because just based on your index files, it has the order information. It has already sorted for you. So you can retrieve your data in certain order really fast. All right, yeah. But hashing, no. Hashing, if you need ordered data, you need to do the sorting. You need to do the sorting, and that's very expensive. Okay, so that's the reason if we can apply the binary search, that we try to use the binary search first. Only we cannot apply binary search, no total order, then the only way we can take, that's the hashing way. Okay, that's the hashing way. Yeah. Yeah, because we have more other requirements than just the fast search, right? Other than fast search, we, in our queries, we have many other requirements we need. And the ordered index files most convenient for our all query operations. Think about that. Okay, yeah. No. All right, ordered files, yeah. Tree data structures, yes. All right, so here, another important improvement on the structure, tree data structures. Yeah. Here, before we consider tree data structures, we imagine our records is arranged in a straight line, right? Ordered in a straight line, all right? Yeah. But in this situation, in a straight line, although you apply the binary search, but still, if the data number of rows too big, you need to apply many comparisons. Yeah. Here, the DBMS try to find a way to reduce the number of comparisons. So it feels, so this line structure still not very efficient. So it uses tree structures. Yeah. So one level, next level, another level, okay, in multiple levels. Each level is one line, okay? Each level is one line, or ordered, but you may have multiple levels. Then you have a tree. Think about that. Then you use a tree structure. This tree structure, the benefit of this tree structure, even you have huge amount of data, you can use very small number of comparisons to find the data at anywhere in the tree. Okay, yeah. All right, so that's the idea. Yeah, multi-level indices. So we call them multi-level indices. Okay, yeah. Dynamic structure. Another important property for this, it has the dynamic structure. What do you mean dynamic structure? Because in a table, we know data comes in and out, right? Sometimes you insert a new data item. Sometimes you delete one. When you do that, you need to modify the structure. When you do those operations, how can you still maintain the order information in your index file? Do insertion, you break the order, right? You need to fix it. The fix operation should be fast. When you fix the order, that operation should not be very slow. That's the requirement. When you make a deletion, you make a deletion. All right. Do you need to rearrange your tree records? Sometimes you need, sometimes you do not. Right? But sometimes the reason you need to rearrange because you want to, after deletion, your data amount becomes smaller and smaller, right? So you may want to make your tree smaller and smaller. All right. Otherwise, small amount of data, you still use a big tree. That's not good. Right? You waste a lot of space. When you make the deletion operation, when your tree becomes smaller and when your tree contains relatively small amount of data, you need to shrink your tree. Okay, make your trees smaller, shrinking. Okay, so those operations pretty complex, pretty complex. Okay, yeah. If I have a chance, I will show you those two algorithms: insertion algorithms and the deletion algorithms. But it's very complicated. Yeah, just let you know. The algorithm could be very sophisticated. Very sophisticated. Okay? Yeah. So if I have a chance, I will show you. You know, animation, all right? Diagram, you know, show you how to change the structure of this multi-level index trees. All right. Dynamic. So that's, we can maintain dynamic data. All right, then hashing, hashing, okay, yeah. Fast, but no order information. Yeah. It has the big drawback, right? Yeah. Otherwise, if it does not have this big drawback, then we should always use hashing, right? But not, yeah, this one, the sacrifice is too big, okay? So we do not want to sacrifice our order information in exchange for this little faster performance. Okay, yeah, so that's the hashing, yeah. All right, how indexing works. Yeah. Now, to find a record in a table, yeah. So we learn more and more information about indexing. Okay, yeah. How to find a record in the table, in our original table. Okay, yeah. A search condition based on a field. And then let us assume we have an index file based on this field. How about that? Yeah. We need to create an index on this field. Then you can do the search operation, you know, if you have a search condition based on this field. Yeah, all right. Assume that an index is created on the field. Yeah, okay. So otherwise, if you do not create an index file, then you cannot enjoy this fast search performance. Yeah, usually for small database, then people do not bother. Because we do not have a lot of data. So the benefit is not big. Okay, the benefit is very little, but only when you have large amount of data. Then it's better to use indexes. Yeah. All right. The index is searched. Yeah. Now, when you do the search, do not search on the original table. Okay, go to its corresponding index file and do the binary search, because on the original table, you cannot do the binary search. Now, so you jump to the its corresponding index file. Now you can do the binary search. Yeah, very fast. You can find the location of the record. The search result will return the storage location. What's the storage location? Pointer. On the hard disk, you have an address on the hard disk, right? So your index file will store the pointer, point to the address on the hard disk location. Yeah, so you know where to find it, where to load your data. Yeah, yeah. So yeah, we will get more details on the structure of index file. Yeah. Search result of the index file. What's the search result of index file? Yeah. A pointer to disk block. Here we need to have a disk block concept. Disk block, okay? Yeah. That contains the original requested data. All right. Here we need to know the hardware a little bit. Disk, okay? Yeah. Let's assume, so this is one because there are many slices, one slice, two-sided disk. So, and we store data in many concentric circles. Many concentric circles. Okay, all right. Then it's also divided into sectors like that. Into sectors like that. Okay, yeah, organized. Yeah. Then still, so on each ring, each sector still blocks. Okay, yeah. Many blocks. Okay, divided into many blocks, disk blocks, unit. Okay, yeah. And this disk block unit, that's the unit we load from hard disk into memory, main memory. Disk block, okay, or page. Yeah, sometimes people call page block. Yeah. So that disk block, yeah, every time you load a whole block of data, when you load the data from hard disk to main memory, load a whole block of data. The reason is simple. The reason is simple. If you only load one record, one row, that's a very small amount of data. If you only load one row of data, we know one visit from memory to hard disk is very expensive. One visit from memory, main memory to hard disk, that one trip is relatively slow. Yeah. So one expensive trip, you don't want to carry just one record of data. So you want to carry a little more data, right? Reduce the number of trips. In order to reduce the number of trips, then each time you load a relatively more data, that's a block of data. Whole block. Whole block may contain multiple records. Several, not just one record. Yeah. Many records. Okay, yeah. In that way, if next time, if you want to get another record from the same block, you do not need to go to the hard disk another trip because you already loaded, right? Yeah. So reduce the number of trips to the hard drive. That will improve the performance. Yeah. All right. Here. Yeah. Here, a pointer. So you only need to point to that location of the disk block. That's enough because the whole block will be loaded. You just point to that block. Okay. After that block of data is loaded into the main memory, then you do the linear search inside the block. But that's inside your main memory. Inside your main memory, yeah. Think about this procedure. Okay, yeah. All right, yeah. So that is our 8.2. Yeah. So we finished that part. But still, at this point, we just learned a high level structure understanding. Yeah. Then we need to go down a little more next a few times to learn a little more structure, but we won't go to too much deeper. Yeah, just enough. Yeah. Just enough. Yeah. This kind of background knowledge. Later, you know, inside hard disk, DBMS. How does the DBMS store data inside a hard drive? You just have that basic knowledge. That's enough. All right, yeah. So let me start right here for this is the beginning of module 5, and since we just complete module 4, I need to give you quiz number 4. Okay, yeah, quiz number 4. So then, so you have 4 quizzes, 1 homework assignment. The second assignment I will give you next week. Next week, when we near the due date of first assignment, then I will give you a second assignment. Near the due date. Yeah, let me put this date, in our Wednesday's class. In our Wednesday's class, my homework assignment number 2 should be almost there. Yeah, almost there. Okay. All right. So let me stop right here.